All right, this presentation is about APSViz, which stands for the ADCIRC Prediction System and Visualization. APSViz was created by the Earth Data Science team at RENCI, along with external collaborators. Brian Blanton, the lead of EDS Group, was the PI on this project, along with Rick Lutek, who is a principal developer of the ADCIRC model. Its development was funded by the Department of Homeland Security, Coastal Resiliency Center at UNC. I would also like to recognize my other teammates, Lisa Stillwell, Phil Owen, Jeff Tilson, and Matt Watson. And finally, this presentation was created from existing presentations by Brian Blanton and Phil Owen. So I want to acknowledge that and specifically thank them. EDS motivation in creating this system was to support their ongoing work of producing storm surge forecast with the ADCIRC model. APSViz is primarily focused on hurricanes, but also produces synoptic forecasts and acquires other data sets that over time can be used in other types of studies. More broadly, EDS is also studying long-term risk-based events such as the impact of climate change and emerging issues such as compound flooding. The computational challenges in predicting storm surge are real-time and operational constraints, primarily in getting the data and processing it on time. ADCIRC grids are large and require a lot of time to produce a forecast. There are multiple collaborator ensembles, each of which can have their own grid type, which requires a system capable of inter-process communication, a GPU hybrid environment, and the spawning of hundreds of Docker containers. The physics challenges in modeling storm surge are processes that interact with each other at different spatial and temporal scales. These include, but are not limited by, wind-wave coupling, riverine coastal interactions, compound flooding. The first is done by integrating the SWAN model with ADCIRC, while the latter two are currently areas of research. In case you aren't already familiar with it, ADCIRC is a numerical model that solves the shallow water equation for tides, storm surge, and wind waves using the finite element method on linear triangular elements. ADCIRC forms the base of APS, or the ADCIRC Prediction System Pyramid, which is a collection of software layers that coordinate the application of the ADCIRC storm surge model for real-time weather-driven prediction of coastal hazards. ADCIRC uses a triangle grid or mesh, which complicates additional visualization and analysis approaches. Above ADCIRC, APS uses ECMWF EC-Flow as its workflow management system. It orchestrates ADCIRC simulations on high-performance computing resources, producing all of the ADCIRC output data sets for both the nowcast and forecast. And finally, APSViz itself is the workflow that coordinates most processes of the ADCIRC EZ-Flow output into geospatial formats for downstream use. It also includes the acquisition, processing, and ingestion, tidal buoy, river station data into time series database, as well as the spatial downscaling of ADCIRC data. It enables the rapid and efficient visualization of APS model output that is critical for real-time decision makers facing threats from coastal flooding, high winds, and wave impact. APSViz is a cloud-aware software stack that includes open source and custom data processing tools. It has been installed fully on AWS, which was a requirement due to the possibility of electrical outages at RENCI during a hurricane. ADCIRC requires a large amount of information for predicting coastal hazards. Coordinating the numerous data input outputs and high performance computing job scheduling is complex. Workflow managers have been written to manage this process. Both ADCIRC and APSViz are community-driven, contributing to both research and emergency management. Users such as the Water Institute of the Gulf, associated with LSU, University of Georgia, and the Texas Advanced Computing Center, run ADCIRC models and contribute nowcast and forecast directly to APSViz. APSViz provides them with a platform where they can directly compare their results with each other during a storm event. The ADCIRC data produced by these groups is available through a Threads data server, and organizations such as NC and SC use this data during storm events. ADCIRC support tools, or AST, gathers water levels at wave height data and wave height data from NOAA tidal gauge stations, offshore buoys, as well as water level and stream elevation data from North Carolina and USGS tidal gauge and river gauge stations. This data is further processed, so it is time synced with the ADCIRC model output, and water levels and wave height are extracted for each station location from the ADCIRC nowcast and forecast. These tabular data are continually ingested into a Postgres timescale DB and served to the APSViz web interface front end, allowing direct comparisons of ADCIRC model data with in situ measurements. Kalpana is a Python GRASS GIS-based downscaler, which was developed by Thomas Suevas, a student of Casey Dietrich, who leads the NC State Coastal and Computational Hydraulic team. Kalpana reconciles ADCIRC solutions with high-resolution DEMs by considering small-scale topographic features. Kalpana can downscale ADCIRC maximum water elevations to a higher resolution raster. This process can provide a more accurate representation of the extent of inundation. As part of the downscaling, the water surface can be expanded outwards to intersect with the ground surface beyond the extent predicted by the ADCIRC. All of this infrastructure accumulates in the front-end web interface, providing a flexible, extensible framework for visualizing ADCIRC and related data. This system uses state-of-the-science cyber infrastructure, which is entirely open source. All components are containerized, making it cloud-ready. It is fully open source, and the original ADCIRC data layers are all accessible externally via TDS or S3 buckets. Currently, the future of APSViz is uncertain. Its original source of funding from FEMA no longer exists, with the entire Department of Homeland Security Coastal Resiliency Center at UNC being eliminated. We have submitted some proposals, but that process is stalled for everybody. We are continuing small improvements, most focusing on using AI retrieval augmented generation, more commonly known as by its acronym RAG, to enable the searching of our data in relation to external sources of information. We are continuing to look for other possible funding sources. And that's it.
So I am curious about this, in that this is a project using the digital elevation model. I don't know from when, but how would you suggest a person to use a data set that's meant for coastal surge modeling, as some of this information also changes over time? The digital elevation.
Yeah, the digital elevation model data that we used, we did this for North Carolina. And so North Carolina collects its own DEM data, and it updates it periodically. And it's at very high I think it's actually we could have gotten it at a higher resolution, but we actually had to reduce the resolution because of the time it would take to process it. But as I recall, we used 10-meter DEMs, and those are all the North Carolina data is available through the state. And then this actual method, one of the main steps is that you have the original water level in the ADCIRC grid, which is an unstructured triangle grid or a mesh. And so there's a step in which that information is converted into a vector file, a GIS vector file. And if you notice, you can see kind of how this is the original, this is like the ADCIRC raster that we produce for the website, and that's a coarser resolution one. But in this step, it's using the original ADCIRC gridded data and converting it to a shape file or a vector file, and you can kind of see how you have these polygons that look like polygons, and then the DEM is used along with that vector file to downscale it to a raster format, and that's the step that's actually done by GRASS. So if needed, I could provide you more information on it, and even the GitHub URL to Kalpana itself.
Okay. I might follow up afterwards, but I think I
Okay.
might have to study some of the different software here. My question, I think, is for longitudinal research, where some of this is built on like premise of the digital elevation. If it's built on it now, and then the things 10 years from now it looks different, how does that get recalculated, or how would you use this as a cross-sectional representation of this current time and landscape?
Yeah, I think that's a broader issue, and one reason why the state, especially in coastal areas, but throughout the state, I think they update it every 5 or 6 years. So there's an attempt by the state, especially in coastal areas because of things, the hurricanes, to update the DEMs that they have, and the original kind of driver to the state getting in the DEM business was, as I recall, Hurricane Fran, that they came to the conclusion that they had to start collecting this information and do it at a high resolution. So, but that's if you're doing it in other areas, that's could be a more significant problem if the DEMs aren't updated.
Thank you.
You're welcome.
What kind of operational tempo is this data delivered on? I mean, like what is the timeline between the forecast of the storm surge to the downscaled Kalpana product, and how often is it updated during an event?
It's 6-hourly data. So every 6 hours they run they go through and run the model completely. And
who does this data get delivered to when it's produced?
Well, we have the access through the website, and but then also we have these TDS servers, and so the North Carolina Department of Transportation, and in the past, South Carolina Department of Transportation would acquire the base data from the TDS servers and use it for their own purposes. North Carolina has this Feynman web application, and I think some of our data may be used in that, as I recall. But then you have these other organizations like the Water Institute, which are running models and then also retrieving data. And as far as their specific uses of it, I'm not sure. They're collaborating on this part, but they have probably other things that they're doing with the data. And there's some, they are like the Water Institute, especially, actually has a lot of their own systems, and they were key in developing utilizing EC-Flow, where one of the key people who developed our converted EC-Flow to work with ADCIRC came from the Water Institute.
Thank you.
Go ahead, Jimmy.
Okay, so follow up to that last question about like what kind of data is being used in this modeling. Is this just water flow and water height, water amount, or does it also have chemical testing or I'm blanking on the phrase. Does it have ephemeral data collection to monitor contaminant levels?
Yeah, it's nothing like that. It's water level is one of the primary things, but it has wave height information. There's other variables that ADCIRC produces, and we're only actually on the interface, we're only showing a handful of those. ADCIRC produces a lot more when it runs, and those data are available through TDS. But for your type of application, I know that people have used ADCIRC for the type of application that you're speaking of. But that it would be a case where it would just be one of the components in their larger model.
Right.
And so I'm pretty sure that if you search on ADCIRC and those topics, you may actually find some papers that people have done that type of work.
Yeah. Thanks.
I'm curious about the verification process and if what events has it performed really well on versus events that it maybe hasn't performed as well on, if you have anything in reference to that.
Well, one is we run it in these two modes. We have a synoptic mode, which is just regular weather. And then when a hurricane occurs, we have a tropical mode. And in the tropical mode, we're going in and we're grabbing information about the tropical storm from ECMWF data. And then that's used within the ADCIRC model to recreate the hurricane. And it is something in which that's kind of the mode that ADCIRC is really designed for. But in the synoptic mode, sometimes you have like a northeaster, and those can have storm surges. But because we run it in the synoptic mode, so we don't have this specific central coordinates of the extratropical system. It's less accurate. And then even if we try to implement extratropical system like we do a hurricane, it tends not to work as well. So so that would be kind of some of the areas that we're kind of trying to push the model in improving it on is looking at non-tropical storms that are significant storm surge producers in a way that improves what we currently can do with just synoptic runs.
Sure, I'll Since Dave's not here, I'll ask a Dave Jones question. I'm just curious about the output data services. Are there online services do you do this continuously, or does this have to be run sort of on request when a
We do it
event happens,
continuously.
and
Yeah,
then
we're okay, sorry.
well, and then it's so if there is, are there services that things like GeoCollaborate can pick up on?
Yeah, and I think so. And one we do it continuously, although right now we aren't because uh, when we aren't in hurricane season, we don't run it on AWS. We have a local machine that we're running on, and that machine is in the process of being moved, physically moved. And so we aren't able to actually run uh, the ADCIRC model and get the data. But the website is still there. It just doesn't have any data. But otherwise, we run it all year long. Most of that time it's run in the synoptic mode, and the data is available through the TDS servers. And I could give you the URLs for the main one, but it's also something where in the long run I've been pushing the idea of using Stack as a way to give more accessibility to the data. And that's something that hopefully if we can keep this thing going, that would be one of the next things we would like to provide users are Stack catalog files in which they could search and pull the data from the TDS server.
I have one more question, and that's, I know you had mentioned that a lot of emergency managers use this information, and I'm assuming other stakeholders. Have they given, you all any feedback on the model or like areas, that like, or other variables that they would be interested in seeing from this model? Yeah.
Yes, and I think the key thing there is kind of the areas of research that we're looking at, and the key one is the impact of precipitation on flooding, and then how that interacts with the storm surge along coastal areas. There's been a lot of work in that area, and then and in broader, just the interaction between river flow, and the storm surge. So those are some of the key active areas that emergency managers and transportation planners are interested in us pushing the model. And we have a group that's pursuing that, but there's other groups. I know the Texas Supercomputing Center, they have a group pursuing that, and I've heard of other groups doing it as well. So it's kind of the area that's getting a lot of attention now.